Hello, I'm Alexander Efimyevsky. Nancy Wang and I are going to present the table extraction part of our tutorial. Table extraction consists of two main tasks: table region detection and cell structure recognition. Table extraction has been studied for more than 30 years. In the beginning, most approaches were top-down methods where you start with a page and then you identify graphical or ruling lines on the page and group them into ruling line grids, which then used to identify tables and cells. You can extend those approaches to white space lines or virtual lines in addition to ruling lines. Later, people used bottom-up approaches that are based on clustering text into larger units, such as rows, columns, or some paragraph-like units, blobs, using spatial information such as gaps, overlap, alignment, as well as table-specific keywords. Starting from early 2000s, machine learning algorithms became popular. One way to use machine learning is to identify rows on the page and then classify them into table rows and non-table rows using a collection of features. People also defined probabilistic models for tables and used graph-based machine learning to identify cell structure within a table. Starting from mid-2010s, deep learning became the algorithm of choice. One way to use deep learning is to take an image of the page and then use a convolutional neural network to detect regions that correspond to tables and cells. You can also use graph neural networks to identify rows and columns inside the table, and natural language embeddings to group text according to semantic relationships into cells. How to build a table extraction system? What are the common subtasks? Of course, table extraction, table region detection, and cell structure recognition are the two important subtasks. But before doing that, it helps to do some pre-processing steps, which we can group into an analyze page subset. If it's an image, then you need to detect text on it and graphical lines, identify some low-level structures and layout information, and then take shortcuts if there is obviously no tables on the page. After you detect tables and cells, it often helps to do some post-processing, such as identifying false positive tables and throwing them away, resolving ambiguity, whether it's one table or two tables on the page or multiple tables. Sometimes all of these are possible and we need to pick the best one. Adjust table structure or table border based on some rule set and apply customer specific rules to attain better accuracy on tables, specific kinds of tables that customers are interested in. So now we have three groups or subsets of tasks: analyze, detect, and refine. Within the analyze subset, some of the subtasks are letter and font detection using OCR, optical character recognition, then page layout detection, grouping text into larger units, rows, columns, or paragraphs, and detecting separator lines, such as graphical and white space lines. In the detect subset, the common tasks are table region detection, cell detection, grouping text into cell units, and then identifying rows and columns, the relationship between cells inside each table. In the refine subset, the common tasks are score tables, assign some confidence value, filter false positive tables, resolve ambiguities, whether it's one table or two tables, or where exactly is the bounding box of the table region, adjust tables if necessary, or cell structure inside the table, and handle special cases that are customer specific, apply a rule set to improve accuracy on customer specific documents. If you are using machine learning, then there is a set of subtasks related to learning infrastructure, such as defining accuracy metrics for tables and cells, labeling ground truth tables in the documents, and implementing a user interface for customers to provide feedback, as well as a mechanism to incorporate this feedback to improve accuracy on customer-specific documents. So let's go to the first subtask, letter and font identification. PDF documents can be scanned, programmatic, or hybrid. Scanned documents, of course, are images. And for the images, we need to use optical character recognition. But before you run it, often you have to do additional pre-processing steps. Documents often have low resolution, fuzzy text, have a distortion or rotation. Text can be tilted, and there may be noise present, such as manual, some signatures, or stamps, barcodes, or simply some blotches of paint, some blotches of ink on the document. If there is low resolution, then you have to enhance it before you can apply OCR successfully. Then after you apply OCR, there are additional pre-processing steps due to the fact that even if characters are identified reasonably well, font information often is not well identified. Even font size can vary across the same line of text due to low resolution and the fact that different font types may result in different size. In addition to characters, of course, you need to identify ruled lines and colored boxes. Here's an example which shows that such pre-processing steps are required. So these scanned documents are either rotated or tilted, have low resolution, fuzzy text, highlighting underneath text, and other features that are combined with text, blotches of ink. So all of these have to be taken care of if you want to achieve high accuracy. Now, for the programmatic PDFs, you might think it's straightforward, but not so, because often you have, first of all, of course, you don't have table markup, you just have characters themselves on the page. But not all of the characters that you read from a programmatic PDF are actually the ones that are going to be printed. There is going to be, sometimes you will see white on white text or colored on colored that is not printed, or text that is out of range, or sometimes the same text occurs multiple times to achieve some effect, such as bold. If you are planning to use image-based convolutional neural network, then there is a reverse task of getting an image from a programmatic PDF. So next subtask is page layout. Plain text often comes in 2-column or 3-column layout. If you don't detect it, you may identify false positive tables just because plain text has a complex layout. Pages often have footers and headers that have structure in them, may come across as a table. Lists often may look as a table, especially if they are hierarchical. There may be charts present and the text may be highlighted. Section headers may also have a hierarchy to them. So all of this can be identified at the pre-processing stage. It helps to identify some data structures that will help subsequently to be more efficient. For example, if you use alignment in table detection, then you can build data structures that will answer queries about which text is aligned up to a certain tolerance level. And for clustering by distance, you can build spanning trees to make it efficient. You can also detect deep learning features such as natural language embeddings for text that will help you group text into larger semantically bound units. Here's a running example for this part of the tutorial. It's from a financial document. There are two tables in here, which may not be obvious because column headers of those tables are numbers. So in this example, I show how text is aligned according to X coordinate. One algorithm for detect layout that was used since 25 years ago or more is so-called recursive XY cut. This algorithm takes a page of text and then projects it on X-axis and Y-axis and looks at the density of the projection, finds dips in the density, and then partitions text on the page into blocks according to those dips in density. Then for each block, it recursively runs the same algorithm until the entire page is partitioned into a tree of blocks that represent page layout. It's important to take shortcuts early on to avoid running an expensive deep learning algorithm if there are no tables on the page. The majority of pages in documents don't actually have any tables on them. So if you can detect early that there are no tables and then jump all right to the output, you will save a lot of computation time. You can save even more computation time if you detect obvious non-tables, and then if there are no other structures, then you jump to the output. And if you detect some very easy tables, such as ruling line only tables, and find that there are no other structures, and again jump to the output. Next subtask is going to be grouping text into larger units. Many table extraction algorithms group text into larger units. Could be those that group text into columns, those that group text into rows, or those that group text into blobs or semantically bound paragraphs of text. Of course, not all algorithms do that. Some rely on white space and ruling lines only. So in this running example that contains two tables, this will be the columns. These are going to be the rows. Notice that some rows have multiple lines of text in them. And this could be multi-line blobs. Of course, most of the entries in the table are typically single line, but there are some very important entries that are multiple lines. And if you fail to detect those multi-line entries, then you will get the incorrect result. One example of a system that uses columns first approach is Tesseract. It is the way it was in 2010. So Tesseract groups text into column fragments. Of course, when it groups text into column fragments, it doesn't yet know the table boundaries. So these are not going to be complete columns, but only fragments of columns. Then the column fragments are going to be grouped horizontally into table fragments. And finally, those table fragments will be merged vertically if their column fragments match into tables. So let's use our running example. First, we detect X-axis alignment information. Then we use that information to group text into column fragments. Then we group column fragments into table fragments, and then merge table fragments that match across column fragments into tables. As any algorithm, this approach has its shortcomings. For example, if you have multi-column headers that are not aligned with column fragments, you risk missing them or not including them into a table. Another approach would be starting with rows. The first machine learning algorithms for table extraction used that mechanism. In that approach, you start by identifying text lines on the page. And then you use machine learning classifier to label text lines into lines that belong to tables and lines that don't belong to tables. But often you need more than just two labels. In the case of multi-line rows, you will have to label some lines as incomplete rows and others as complete rows, and then merge incomplete into complete. The actual classifier that you're going to use, you can choose any one of the well-known classifiers, such as support vector machine or conditional random field or any other. And you have to define a vector of features, of course, for your lines in order to apply the classifier. So an important step will be to merge incomplete rows into dense rows to compute complete multi-line rows. Here's our running example. So some of the rows in this example, a machine learning algorithm will label as dense rows. For example, those that contain multiple entries with long spaces between them. Other rows will be labeled as sparse rows, incomplete, which have to be merged into dense rows. Other rows may be labeled as table header rows. Then we have to detect an alignment direction, vertical alignment direction. Do we have rows that are aligned towards the top, or aligned towards the bottom, or aligned towards the center? This will affect how we're going to merge incomplete or sparse rows into dense rows. And then the final step will be to merge those sparse rows. However, we have to be careful because some sparse rows actually do not form multi-line rows with the dense rows, but they may stand on their own as headers of a table section. So additional labeling may be required to separate section headers in the table and then merge them between themselves only rather than merging them into dense rows. So yet a third way would be to identify semantically bound units of text first, which we can call blobs. Other papers may use different terminology. So phrases, text lines, paragraphs. A blob is can be a single line or multi-line. A blob has to belong to only one cell of the table, although one cell may potentially contain more than one blob. Some blobs, of course, may just be plain text and don't belong to any table. Identifying blobs helps a lot with cell structure recognition because you will prevent oversplitting cells or undersplitting cells. So detecting blobs is non-trivial. You cannot just rely on spatial information. This is a contrived example here, but it has the same features as many real-life examples. In the case of multi-column headers, it's often very difficult to say whether they where the one multi-column header ends and another begins. Just using spatial information, you may not be able to resolve this. And the same applies to row headers that have multiple rows, multiple text lines in a row. What are the approaches to detect to detect blobs? One we have already considered, which is the labeling of the rows and then merging sparse rows into dense rows. Another would be to rely on reading order detection, which is in itself a significant challenge. You can also define a machine learning classifier for blobs. So a blob, you can map a blob into a vector of features and then apply classifier to compute your confidence score, whether it's likely to be a blob or just partial blob or a union of multiple blobs. Some features that you might use is how the termination, whether a blob terminates, the text inside the blob terminates with a dash or an article or something that is not supposed to be at the end of a complete piece of text. Or if a blob contains one or multiple numerical values in it, multiple numerical values may mean that it's not one blob, but multiple blobs. Indentation, of course, is a feature. You know, the paragraphs have a peculiar indentation that is a detectable feature. And font properties. Text within the same blob tends to share the same font. You can also use deep learning approaches to detect blobs and cells. And you can use convolutional neural networks, or you can use embeddings in order to semantically link, identify which text is semantically linked and which is not. So here's an example that shows again that it's non-trivial to detect blobs, especially in the case of row headers and column headers. Naively, you might detect each line on the left-hand side as its own row header based on the dense and sparse rows on the right-hand side. But if you use semantic information, then you'll have to merge multiple lines on the left-hand side into a multi-line blob. So semantic information is important to take into account. Finally, a subtask, another important subtask is detecting separator lines. Of course, ruled lines are critical. If they are present on the page, they typically carry a significant information about table boundaries and cell structure. Ruled lines may be non-trivial to detect because they often have gaps. And if they are colored boxes, then you have to decide when colored boxes have to be merged together and when they represent separate cells. However, even after you detect graphical lines, even if they form a perfect grid, it may not necessarily mean that you can rely on them to detect cells. So here is an example of tables with a perfect ruling line grid, but they don't define correct cells because some of the lines are not ruling lines, but are white space lines. In other cases, ruling lines don't extend all the way to row headers or column headers. If you just use ruling line grid, you might completely cut off row headers and column headers from the table. And of course, there could be some very sophisticated examples where it's essentially a piece of art rather than a table. And then ruling lines are not sufficient to understand what it is. So in addition to ruling lines, in that case, white space lines are also critical. A way to detect white space lines typically is to generate all possible white space lines and then use some filtering condition to only only identify the subset that matters for table extraction. In order to score white space lines, you will have to use some features. Two kinds of features that are important is what kind of text is present on each side of the white space line, and the features of that text, such as alignment and size and some contents of the text, as well as whether one white space line overlaps with other white space lines. Because inside tables, you typically have lines that form a grid. Okay, so now I hand over to Nancy for the detect subset of subtasks.
Hi, everyone. My name is Nancy Wong, and I'm a researcher at IBM Research Almaden, here to talk to you more about table extraction. As Sasha has led you through the analyze stage, where we try and find smaller elements that are helpful in doing table extraction, I'm in my section in the detect, I'll talk about the larger elements such as table region, cell boxes, and how to get the row and column relationship of a table. Let's start. So first of all, for table detection, I'm going to break things down a little bit by time. Before the deep learning era, in the past decade or so. A lot of work has been around finding elements that are related to tables and then grouping them to find where the whole table is. So, and this could involve finding rows, columns, blobs, or lines first, and then grouping them. A lot of the newer work using convolutional neural networks, and a majority of them are based on object detection. Which is trying to find a fixed set of table region proposals from the neural network for the object, which in this case are tables. And because CNNs share computation features across all translations of a given proposal rectangle, it can work very quickly if you're given something like a GPU. And in this case, the proposal rectangle shapes and sizes are fixed as hyperparameters, and this can actually be very important in your final table extraction quality. And if a proposal hits the table, then a regression step will decide the actual table border, so how much to regress beyond the fixed anchor tables, the anchor boxes. To detect candidate table regions in a pre-deep learning era, one way is to looking at ruling line grids or frames and their connected components. You can first look at the rows, stack the table rows where they co-align, and then a machine learning classifier can label the actual rows. And then for the column first method, you can first cluster the overlapping column fragments, and then you can group the table columns horizontally and then stay within the page layout columns whenever possible. And you group them if the fragments overlap, match, or subsume. But in both cases, the header areas can require special handling because they do look a little bit different from the rest of the table. Another method is to classify text blobs and try and cluster the ones that are labeled table. And given the neighbors labels, you can iteratively label a certain piece as a table. And you can also train a kernel logistic regression classifier to do this task for you. Another way is to find the strong separator lines and find a grid. In the trivial case where tables are fully graphical line, meaning that for every cell, they have an explicit line to outline the cell. This is trivial, where you can find areas where the lines are overlapping and crossing with each other. But in most cases, tables don't always have graphical lines, or they may only have a few. So in this case, you can still find strong separators based on parts that don't have any text between them. And you can bi-cluster these intersection matrices of the horizontal and vertical separators. And here is one interesting example of using non-negative matrix factorization for grid clustering to figure out the location of tables. And finally, the more recent work, as I mentioned earlier, use existing object detection frameworks such as faster RCNN or YOLO, and then fine-tune them using some table data to detect tables as the object. And as I mentioned earlier, the convolutional layers will ingest the image, so whatever format it is will be converted into an image. And then the proposal boxes there will be a classification step and a regression step to get the final proposals. And there can be additional post-processing as well, depending on the work. And I've tried to list as many as I could of the recent methods that use a variant of this in one way or another. but each one do have a little bit of a spin on the generic fast RCNN or YOLO, so I highly encourage to check those out if you're interested. I also want to talk a little bit about our method coming out of our group at IBM. We call it GTE table for Global Table Extractor. And it's still similar to what we said earlier, adapting the idea of object detection for table detection. But in our case, we leverage the spatial containment relationship between tables and cells to improve this process. And what we mean by that is we know that cells need to always be inside tables, and tables cannot exist if it doesn't contain any cells. So leveraging this relationship, we can actually explicitly add an extra penalty loss when certain tables are detected without a lot of cells in there. Similarly, these detected boxes using another network can be used in the input to help improve the detection of tables. And it's better to separate this, as you can read more in our paper, rather than having one model that tries to detect cells and tables at the same time, because their shapes are very different in aspect ratios, and it's very hard to come up with a set of proposal boxes that will be ideal for both types of objects. And also, not all data sets have both, so this is a good way to be able to train two separate networks, but are still connected using a penalty loss. Next, I will talk about cell boxes in table extraction. Now, this is not something that is always done. There are only some works that explicitly try and detect the cell boxes in doing the table structure identification. Overall, in the pre-deep learning approaches, they generally just use text blobs as cells, and then some of the works try to merge these blobs that share columns and rows, or use separator lines to try and figure out if different text blobs belong together as a cell. In deep learning, there have been a couple works, including ours, that detect cells over images, also using object detection CNNs. And it's a similar concept of fine-tuning these detectors with cell data. And just super quickly, talking a little bit about our GTE cell. It's similar to what I said earlier, where we try and use object detectors to fine-tune on cell data. But it has an extra attributes network. And what that's useful for is that there are many different kinds of styles when it comes to tables. Some of them are fully graphical lines, so there are lines all around every cell or most of the cells, and some are blank. And convolutional neural networks are sometimes weak at figuring out the global context. So when just looking at the local context, given a line, it may not know whether that graphical line is important or not to delineate the existence of the cell. Therefore, we actually have different specialized networks that are specialized for tables with graphical lines and without. And then we have an extra network to try and determine what type of table it is from a global level. And finally, I'm going to talk about how we put these different elements together so we can figure out the actual row and column relationship of all the cells. The cell structure needs to define what are rows and columns, and also the order within each row and column. Another way to talk about this is for each cell, we need to know its row and column position. And there are many different ways to specify cell structure, and a lot of these come from different ways of doing the cell structure extraction itself. One, you can use separator lines to define the cell span across the different rows and columns. You can have a graph over the cells and then define a relationship between different cells as the same row or same column. And cell boxes, in this case, for each of the cells, you would define its row and column span. And finally, it can even be text-based. In this case, you can define the cell structure using structured code outputs such as HTML and XML that you would see on a website, for example. And you can represent that as fully in this text-like format. Using line-based, the cell borders are a combination of ruling lines, and strong white space lines, meaning that it's most likely also meaning to separate different cells. And you can extend these lines to make rectangular cells, and then the lines should be avoiding to cross actual text blobs. In ruling line grids, you want to test for incompleteness. There may be multiple numerics per cell, and a strong white space line can split text in more than 2 cells, and there can be a mini table inside a ruled cell. And cell structure can extend beyond the table frame. So all of these are things that you want to test for, meaning that the table extracted was not quite correct, and there will be more talk about refinement after this section. And for white space grids, you'll want to clean up empty cells. And this may mean expanding header cells to merge with empty cells. So a certain header cell may be hierarchical and have a relationship with multiple cells below it. And you may also want to merge almost empty rows and columns. So these are all post-processing tricks that can help improve the final output of the structure. And secondly, using graph-based methods, these are relatively newer. You can use spatial constraints to find an overlapping DAG over the cells. And more recently, people have been using graph neural networks to find 2 undirected graphs. There's the same row and same column graph to figure out the relationship between the cells. And if 2 cells share an edge, then they share a row and a column. And for the couple of references we have here, they have some interesting differentiators. One is to find the rows and columns, they find the maximal cliques. And for C19, only adjacent cells share a graph edge. So those are kind of small differences in how to use graph neural networks to find the final structure. Another way of using deep neural networks is to use division models. Similarly to how we described earlier using object detection networks, these can also be used to find the rows and columns. And once you have the rows and columns, then you be able to figure out their structure. You can use conditional and generative adversarial networks in a very interesting work in V20, where using the CGANs, they can approximate the table form, and then they use XYCut and genetic algorithm to refine. But essentially, you're trying to hallucinate the graphical table lines, and then other methods to be able to actually figure out the location of the different rows and columns. And there's in K19, they also took an interesting approach of treating the images as a series of time steps. And then they use the recurrent neural network to figure out where the column and row separation points are as they run through these series of time steps. And for another way I mentioned earlier with using cells is if you have already detected the cells, you can actually use the positioning of the cells to do spatial clustering to figure out the rows and columns. How it works here approximately is you can using the detected alignment and the XY coordinate of each cell, you can cluster, figure out the rows and columns by clustering them. And then after the initial row and column split, you can actually merge and split the results of the cells based on textual clues. For example, capitalization, or if there are special symbols such as $signs or percentages, depending on your domain, that might be need to be merged into nearby columns and or rows. And finally, there's a couple of new works that are using language generation to be able to generate the actual structure itself. And this is alluding to what I said earlier by using HTML text. As you can see here, you can actually try and decode using a language model, an LSTM here, to produce the tags that are important, for example, T-head or TR, as well as, in this case, they have a separate cell decoder that tries to decode the text itself. These models have usually an image input, and they are trying to do not only the table structure, but the job of an OCR system as well. And that's the end for the text section of the table extraction section. And next, Sasha will talk to you about how to refine these detected tables and structures, and also handling special cases. I'll be back later to talk to you more about learning infrastructure. Thank you for listening to this section on detection.
Hello again, I'm Alexander. Let's now talk about refining extracted tables and cells. So the first subtask in refining is scoring tables. Why do we need to score tables? Well, first to filter out false positive tables, then detect malformed or incorrectly identified tables and perhaps fix them by changing them to improve the score. Compare alternatives. The same piece of page can look as one table or two tables or three tables, or there could be multiple ways you can place table regions on the page. So to pick the best alternative, you might want to use the scores. And you can also try to improve tables by adjusting them to improve the score. It is challenging to score a table because tables are very diverse. Some of them are small, others big. There can be lots of issues with the table, which if you compute the score, it may influence the score, may lower the score. There may be misalignments, hierarchy, key value pairs and cells, delimiters that are confusing. So a good score has to take into account all of these imperfections and tell apart the ones that show that it's a bad table and those that show that it's a good table, but just an unusual style. It's important to take into account what's around the table as well. Because of course, the question is the table complete? Can you extend it? You have to make a decision between one table versus two tables. So is there an indication that actually it's two tables in one table? Is there can you split it? You can test for splitting. And non-table text can have structure too, so you have to take into account. Here's an example of a non-table that looks like a table. It's just a hierarchical list of this section with section headers. Here is a case where it's difficult to tell how many tables there are. So in this case, there is one table because there is one set of column headers. This is a very similar case, but there are two sets of column headers. Notice column headers are numbers, so you can just use the numbers, whether it's a number or not, to make this determination. And here you have three tables. Again, it's very difficult to tell without knowing what you're looking for. So how to score a table? So you can, of course, first check for patterns that indicate that it's not a table and rule them out. You can aggregate scores across columns and rows to check whether rows and columns are well formed. A dynamic programming algorithm has been used. If you have a probabilistic model to define a table, you can compute probability or log probability for the score. And of course, you can train a neural network to compute the score. There is a number of features that you can use, especially in a non-deep learning scoring algorithm. Columns and rows, whether they are malformed or well-formed. The presence of separators, root separators, white space separators, extent of those separators. You can compare inside and outside of the table to check whether it extends to the outside or some chunks of the outside are inside. Cell structure, look for oversized cells that span the entire table or rounds of empty cells. Content, of course, numbers are typically present in the table, but not always. Customizable keywords or other rules that you can use for content. And you can, of course, use convolutional neural network too. So once you have the score, you might want to adjust a table to improve the score. So adjusting the table allows you to correct errors that come through table detection. You can also use an explainable method. You can have a rule set to adjust tables that can be customized, and you can use it to explain, but you can also customize it to reflect specific requirements for documents that customers are particularly interested in. Adjusting the table may involve merging table with adjacent table or a block of text. It can involve moving a table border up, down, or left or right, split a table into two, or potentially recompute the whole table region by neural network. Or if there is a range of options, you have detected multiple tables and you have to pick one out of overlapping candidates, then you can use the score to pick one. And in fact, this process can be iterated into a whole search tree of candidate tables. Now, if you have a collection of overlapping candidate tables with different scores, there is a task of identifying a subset of non-overlapping tables that maximizes the score. And there are multiple different algorithms. The problem is NP-hard. So it's the full generality is maximum weighted independent set problem. But you can, of course, approximately search for the solution using dynamic programming or greedy approach. Finally, handle special cases. So customers will come to you and say that there is a specific type of table that they want to be almost 100% accurate about. They may also come to you and say, here's a document that you haven't done a good job on, so please fix it. They are not going to label a very large data set, so you may just have a very few cases that you need to train on or use them to improve your accuracy. So it may require you to introduce rules. Rather than relearning your deep learning model, you may have to introduce rules. And so you probably want to have a rule-based part of your system where you can edit rules. You can also debug rules, and you can use rules to provide some guarantees that for a specific document, you will definitely do the right decision. So now, again, handing over to Nancy.
Hi, everyone. Now I'm back to talk about the learning infrastructure. After we've analyzed, detected, and refined our table extractions, we want a way to be able to evaluate the results, but we also want to be able to generate more data for fine-tuning. So I will talk about each of those here with accuracy metrics, ground truth, and also how to involve humans in the loop to improve table extractions. Let's start with learning, the challenges with learning from data. So first of all, the accuracy metrics. In fact, there are lots of different ways to define accuracy of your table extraction for region and structure, and how to account for partial matches, because an exact match sometimes is too inflexible and not necessarily a good way to capture how good a system is. Secondly, to create more data either for evaluation or for training, it is actually very time consuming to create ground truth for tables. You can imagine that it's quite tedious to indicate all the cells, and a lot of data might be needed depending on what model you're working with. And this often requires some sophisticated UI tools that don't always exist. And in fact, humans can sometimes disagree on what's correct. There are some tables where some look like could be 2 tables or 1, as has been shown earlier. And finally, for optimization, especially with some methods before deep learning, there can be lots of discrete and non-differentiable steps, especially with some of the variables. And it may be easier to think of it as learning subtasks, such as row labeling or cell labeling with conditional random field or SVM. There are some works on trying to do global parameter learning, as cited here. But in general, it can be quite hard to optimize such a problem. In terms of accuracy metrics, there are actually quite a few that the community has tried to come up with. One of the first is from the ICDR 2013 competition metrics. In their case, they have 2, one for table boundary and one for table structure. And each of those also have different measures. For table boundary, the concept of purity and completeness are more like exact matches. Purity being you have to contain only what's in the table at the character level. And completeness, you have to include all of the characters that belong to the real table. But they also have a character level recall precision F1 to compare at a finer scale. For table structure, the adjacency relation is what's looked at here. In this case, the advantage is that, as you can see with the table here, even though there were inaccuracies in inserting extra cells, the extra column here, it doesn't, it penalizes the score, but it still treats these ones as correct because the adjacency relationships are maintained. If you were purely looking at the row and column numbers of each cell, then all of these will be counted as incorrect as well, which is, I think, unfairly punishing this result. In 2019, there was also a table extraction competition at ICDAR. In this case, it was much more image focused. And there were also 2 different document types, modern and archival was shown here as an example of an archival document. Because they were in an image format only, characters were not considered. It was all based on the more computer vision metrics like intersection over union at different thresholds. So one of the weakness I would say in this kind of measure is that, say that there's a table and it's unclear where, if there's, for example, here, if there's no text, does that belong to the table or not? And it can be quite subjective. In the previous metric, because there are no characters, it doesn't actually influence the results at all. But in this case, the IUU will look at that and penalize if it's different from the ground truth. The table structure uses adjacency relationships, just like ICR 2013, but instead of where in ICR 2013, they were looking at the cell content based on the text, here it's looking at the IOU of the cell bounding box, which also can have issues, like I mentioned earlier, depending on how tight that bounding box is on the text. And finally, I want to talk about in ICDR 2020, there is another table extraction competition that is set to be evaluated soon, and it is already currently open for test submissions. Final evaluation is in March. And this is based on a couple of data sets coming out of IBM, PubLayNet and PubTabNet. And both of these come from scientific articles. And the PubLayNet is for document layout recognition. So this includes tables, but as well as other kinds of elements like title, text, figure, and list. And it is based on more computer vision-based metrics, and the input is also image. With mean average precision at a certain intersectional reunion. For PubTabNet, there is a new metric called tree edit distance-based similarity. And in very brief terms, it's based on the code of the HTML code and turning those into tree branches and looking at how much editing was taken to get to the result that was produced compared to the ground truth. I encourage everyone who's interested in table extraction and layout extraction to please take a look at these competitions and hopefully submit your results there. And finally, I want to talk a little bit about functional metrics, which in industry actually matters a lot, but I have not yet seen this kind of metric in any of the competitions. And what we mean by functional metrics is that what matters is making sure that for given a header, so this requires the extra ground truth of figuring out what header annotation, given a header, is the key access actually correct? So in this case, for 17.5, it's with an AA and turnover billion. If this was off-shifted to somewhere else, then the final meaning will be changed quite a lot. And that can really affect downstream applications. So this is kind of a way to capture what will really matter downstream. And this was described in the 2013 competition, but unfortunately it was not one of the tasks. So as I mentioned earlier, table annotations are very labor intensive, especially labeling cells or structure. Manual annotation can require a sophisticated user interface tool, lots of time, and you need detailed instructions to figure out ambiguous cases. There's also another way to annotate, and we call this automated annotation. And what happens here is that there are some types of documents out there, such as how PubLayNet and PubTabNet were made, where there is an HTML version out there already, which contains the structured table, and a PDF version of the exact same table or same documents. And we've come up with an automated text matching algorithm so that the matches between the cells and tables can be made so that the PDF table is automatically labeled this way. And as well, we're also working and there are a couple of examples out there where instead of labeling from scratch, you can do manual editing of errors from a table, from a already existing table extraction model, and it takes much less labor that way. And on my final slide here, I just want to list some of the data sets that we've come across for table extraction and cell structure. There are a few here where there is I call it a complete data set because it contains the table boundary, cell boundary, and the cell structure. the newest of which are XNet, which is PubTabNet and PubLateNet, and also FinTabNet, where it's financial tables. And these are really good ones if you want to train an end-to-end model that can do everything. But there are also a few incomplete data sets that we list here where they only contain one or the other part. And that's it for table extraction. Next, Yanis Katsis will will talk about table understanding, and we will also have a section later on where we bring together table extraction and understanding and see how they interact. Thank you.